PT is not
Okay. Good afternoon, everyone. Welcome to Tah Poe Seminar Series 53 and talk number 1. And today our speaker is our newcomer, Dr. Saikat Chakraborty. And today he will tell us about exploring FR gravity through phase space. Please, Saikat.
Thank you. Is the sound clear? Okay. So, yeah. Hello, everyone. I'm Saikat. So, I have just joined as a postdoc here. And here in this seminar, I will talk about some of the works that I have done in my previous postdocs and a gist of it. So my talk title is Exploring FR Gravity Through Phase Space. So let's start. First, some introduction. So all the relativistic gravitational theories we know of, either GR or any modified gravity, they are inherently non-linear in nature. That means they produce coupled nonlinear differential equations, ordinary or partial. Now, dynamical system technique is a mathematical tool to extract some qualitative information about the solution dynamics when the theory is nonlinear. Why? Because there is no generic mathematical formalism to derive exact solutions for nonlinear differential equations. So in this dynamical system formulation, the dynamical system for formulation of cosmology recasts the cosmological dynamics as a phase flow in a suitably defined phase space. So it's like a visualization of the cosmological dynamics, qualitative visualization. I will focus on my talk on FR gravity, which is one of the simplest generalizations of Einstein. One of the simplest generalizations of Einstein gravity. And I will try to give a historical account of some of the dynamical system formulations. Some of the dynamical system formulations that have been introduced for FR gravity in dealing with homogeneous and isotropic FLRW cosmology, because we know the universe at a large scale is homogeneous and isotropic, statistically speaking. Just a brief history of FR gravity. So Einstein gave the general theory of relativity in 1915 or 16, I forgot. But like 4 years later, its theoreticians started to explore whether it is possible to have other relativistic theories of gravitation. And the earliest works can be traced back to Hermann Weyl and Arthur Eddington. And primarily it was driven just by scientific curiosity without any practical motivation in picture. Now fast forward to 1962, these two guys, Uchiyama and DeWitt, they were trying to normalize GR, and they renormalize the GR using quantum field theory, and then they saw that renormalization attempt at one loop level demand inclusion of higher order curvature invariant terms in to the action of GR. And later works also show that quantum corrections from string theory, for example, give rise to additional higher order curvature invariant terms in the effective low energy gravitational Lagrangian, which is GR. Now fast forward to 1980, there comes further physical motivation. So Alan Guth had already proposed the inflationary scenario. So although we have not seen inflation, so to say, but it is still the most favored among the handful of early universe paradigms. Then in 1980s itself, Starobinsky gave a purely curvature-driven inflationary model, which did not require any other matter component to drive the inflation, which is like an early phase of universe that is rapidly expanding. And Starobinsky's model is still quite observationally viable. Then fast forward to 2003, we had by that time already known that the present universe is in an accelerating phase, and which implies that our understanding of gravity in the cosmological scale is not quite complete, because otherwise the universe is supposed to decelerate. So Sean Carroll and his collaborators in a paper showed that this can be explained through a modified gravity, which is where Einstein gravity is modified like this. And although this preliminary model is plagued by instabilities, later on there came other models too, but this shows the importance of modified gravity in the cosmological context. So some basics of FR gravity. GR is given by this kind of an action. I am only writing the gravitational part of the action. And when we modify it to FR, this R part is modified to FR, which is a smooth function of R. And FR gravity is dynamically equivalent to scalar tensor theories, it can be shown, and so it belongs to the Horndeski classification. In metric formalism is where the action is varied with respect to metric only, so metric is the only dynamical degree of freedom. This is also equivalent to Brandt's decay theory, which is another simple modified theory with vanishing Brandt's decay parameter. And I will use metric formalism throughout my talk. And also FR gravity possesses what is called an Einstein frame description via a conformal transformation. What does it mean? So if you give a conformal transformation to the metric, which is like you transform G mu nu to G tilde mu nu via this kind of a conformal factor. So in terms of this new conformal metric, the Einstein, the gravitational part of the Lagrangian reduces to Einstein-Hilbert action. So in this case, instead of FR, there will be some R tilde. Tilde represents the Einstein frame. And of course, at the cost of introducing a new scalar field, and that scalar field becomes non-minimally coupled to matter. And then for physical viability of FR theories of gravity, these two conditions need to be satisfied, like the first and second derivative of FR has to be positive. These are called absence of ghost instability and tachyonic instability, respectively. So let me now introduce dynamical system formulation in cosmology, which is also called the phase space approach of cosmology. So let me now introduce the dynamical system formulation of cosmology, which will be the center of my talk. So mostly we work with homogeneous cosmological solutions, which simplifies our work a lot. Which should I put it out of my pocket? Like I don't know why this is happening. Yeah, whatever. So mostly we work with homogeneous cosmological solutions, which simplifies our analysis a lot, because the field equations, cosmological field equations, becomes coupled nonlinear ordinary differential equations instead of the most general case where we can get partial differential equations. And in absence of exact solutions, dynamical system formulation or the phase space formulation helps us extract physically relevant qualitative information regarding the asymptotic states of the universe. And by asymptotic states, I mean various cosmological epochs that we know about. Now, dynamical system formulation maps the time evolution of a nonlinear system into the phase flow in a suitably defined phase space, as I have mentioned before. And asymptotic states of a cosmological evolutions are obtained as what are called fixed points. I will explain it in my later slide, but for the time being, the summary is like this. So a starting epoch of the universe, where the cosmological dynamics is supposed to start from, that is represented by an unstable fixed point. An unstable fixed point means a point in the phase space from which all the phase trajectories comes out. Then intermediate epoch is something like which is represented by saddle fixed points. Saddle fixed points are points in the phase space such that the phase trajectories all the phase trajectories just comes near the fixed point and then kind of scattered away from it, but no phase trajectory touches this point. And the end epoch is what is called stable fixed points, where all the phase trajectories just end. Everything can be understood better with an example. So let's go to one of the simplest examples, which is the lambda CDM model. This is the well-known model for late time cosmology. And these three equations represents the fixed points. These three equations represents the field equations which govern the dynamics of the universe in lambda CDM model. So H is the Hubble parameter, which represents the expansion rate of the universe. A is called the scale factor. This does not have any dynamical significance, but you can think of it as representing the size of the universe. Rho is the dark matter density. We know all that dark matter is the most dominant baryonic component today. And then lambda is the cosmological constant, which is the leading candidate for the dark energy. And so we have these two equations, and this is the continuity equation satisfied by dark matter. We recast these equations as follows. We introduce these dimensionless variables. We just divide everything by 3h squared here, and then we can recast these equations like this. We have this kind of a constraint equation, an algebraic constraint. So only two of these variables are independent, and we take to be omega m and omega lambda, which are like fractional density parameters for dark matter and dark energy. And we take and k is something that represents the spatial curvature of the universe, whether the universe is flat, spatially flat, curved, or positively or negatively curved. So here we have chosen to eliminate omega lambda using these equation, and we have these two equations. And these two equations are independent, and since this is a two-dimensional system, you can plot it like this. So at every point, this is called the phase space. So at every point, the slope of this line is given by, the slope has two components, dk dn and d omega m dn. So they are given by these two quantities. So for each k omega m, you know the d omega dm and dk dn, and therefore d omega dk, you know the slope. This is this Q2, which is the dark matter dominated epoch or matter dominated epoch. This is the unstable fixed point, which is also called repeller. So all the phase trajectories come out of it. So you may say that this phase trajectories does not come out of Q2. That is because I have only plotted up to like 0 to 1. Otherwise, it comes like this. And then this Q1 is a stable fixed point, or in other words, it is also called attractor. So this is like the dark energy dominated epoch. So all the fixed, all the cosmological dynamics in lambda CDM model starts from a matter dominated epoch and ends in a dark energy dominated epoch. And here for the spatially positively curved case, we do not have an intermediate phase, but otherwise an intermediate phase would be represented by something like this point Q3, which is where the phase trajectories are coming towards it and then scattered away from it. So this is the example of repeller or unstable fixed point, attractor or stable fixed point, which is like past epoch and the future asymptotic epoch of the cosmological dynamics, and this is an intermediate state. Let's now go to the dynamical system formulation for FR cosmology, and starts from the very basic thing, like say vacuum. So in FR gravity, if this equation is still there, but these two equations, there is no lambda anymore because well, it's not a lambda CDM one. There is only one matter component. Okay, so I'm really sorry. This equation should not be there anymore because it's vacuum. So yeah, I'm really sorry. In vacuum, you have only these two equations. There is no rho. Yeah, this equation just does not matter. Please ignore it. I apologize. So here, the very earliest dynamical system approach that was introduced, they were just plain. They took H, R, and R dot as dynamical variables. Then they named it as X, Y, Z, and the constant equation, this equation can be written as a constant between Z, X, and Y, from which you can eliminate Z. So if you know X, Y, you know Z. And the X, Y, the dynamical equations for X, Y, you can obtain using these and this equation, which are like this. So if you, at any particular point X, Y, you also know X dot Y dot. So you know the phase velocity. And then there is also the reality condition, X square being positive, which gives you a constant on the physically viable region of the phase space. Then if you try to find fixed points. By the way, fixed points are given by this thing and this thing going to 0. Like the phase velocities going to 0. So if you are right on top of a fixed point, you don't move from there. If you are slightly away from the fixed point, you can move either towards the fixed point or away from the fixed point or just get scattered away. But if you are right on top of fixed point, the phase velocity is 0. So this is why they are called fixed points. So if you calculate fixed points here, which is given by x dot equals to 0 and y dot equals to 0 and solve, the fixed points you get here that represents either de Sitter solutions or de Sitter solution means rapidly exponentially expanding solutions or Minkowski solutions. And then there are some approaches by which you can find whether this is stable or not, and you can calculate for which condition this is stable. So like the de Sitter solutions are stable for this condition. Huh? Okay, so yeah, if you make x dot to 0, so okay, by star means the coordinate of the fixed point. Huh? With respect to time, yes. Prime. Oh, okay. So here. Yes, that is derivative with respect to r. So it's like if you try to find this fixed point, so you make x dot equals to 0, which gives you this condition. You make y dot equals to 0, which gives you this condition. And yeah, then there is something called Jacobian you have to calculate, and the eigenvalues should be both negative. Jacobian is a matrix, 2 by 2 matrix in this case, and the eigenvalues has to be both negative, which gives you this kind of a condition. So that is a mathematical detail. So I'm just bypassing it. But this is the earliest dynamical system approach that came into picture. What is the limitation of this dynamical system approach? So we got here solutions that are Minkowski or de Sitter only. So we will only get Minkowski or de Sitter solution in this dynamical system approach. Why? Because x dot equals to 0 is basically h dot equals to 0, and y dot equals to 0 is basically r dot equals to 0. So it's either de Sitter or Minkowski. Other important cosmological solutions like power law solutions, etc., that cannot be obtained by this formulation. And also this formulation is singular at the GR limit. GR limit is given by f prime prime going to 0, because if fr equals to r, which is the GR, then f prime prime, the double derivative, goes to 0, and the dynamical system is just singular. So you cannot examine the GR limit here. Traditionally, this formulation came into picture to investigate inflationary dynamics. So in inflationary dynamics, there was no power law solution. solution unless for later models of power law inflation. But the earliest inflationary scenarios were just exponentially expanding ones. So this formulation, I mean, sufficed. And also this formulation, okay. And also this formulation becomes not effective when you have spatial curvature or matter, because there will be explicit dependence on the scale factor. Here there is no explicit dependence on the scale factor. So let's go to the standard, the dynamical system that is mostly used today, the dynamical system approach. This is a standard approach. So here I have written the field equations again, and here I have taken into account matter and external matter. And here people introduce what is called the Hubble normalized dynamical variables. So again, they divide both sides by 3fh squared. And they define an auxiliary variable like this, which is like capital F divided by R capital F prime. Mind it that capital F is the first derivative of small f. Now this quantity is completely a function of R. So given any functional form of FR, you can calculate y over z, which is like R times capital F divided by small f, which is also a function of R. And then you invert this relation to get R in terms of y by z. And then you can, once you get R in terms of y by z, you can get this auxiliary quantity gamma, which is also a function of only of R in terms of y by z. So this is the modified Friedman equation, which can be represented as this algebraic constraint. And then you have dynamical equations for these dynamical variables. Here I have chosen to eliminate k using the constraint equation. And then you have these 4-dimensional dynamical system. Here W is the equation of state parameter P over rho. And see, here is this gamma, but the gamma, as I said, can be represented in terms of y over z. Let's compare the earliest approach and this approach, the standard approach. In the earliest approach, we got only de Sitter or Minkowski solutions, but in this approach, you can also get power law solutions. And as a concrete example, let's consider the phase space of R to the n kind of cosmology. I mean, phase cosmology in R to the n kind of gravity. This is a, you can say, a monomial kind of gravity, which is like a high curvature limit of R plus alpha R to the n gravity. You can take this to be just R to the n. So in general, phase space of R to the n cosmology in the earliest approach, this will in general be 3-dimensional, unless you consider spatially flat case. But here, with the standard approach, you can always, I mean, it is always 2-dimensional. So it kind of reduces 1 dimension because by the introduction of this new approach. And how does this do it? So for example, take the R² gravity phase space in vacuum and spatially flat case. So you see, there is no single fixed point. There is a line, there is this line, and all the nearby trajectories are coming to this line. So this line kind of behaves like a line of fixed points. So there is no single fixed point, there is a line of fixed point, which is called a one parameter family. But if you take now the standard approach, first of all is vacuum, omega equals to 0 is still there, but you do not need the special flat case. This entire line is reduced to a single point. So whatever dynamics was represented by this line is reduced to this point. And see, this point is an attractor. All the phase trajectories are coming to it, just like all the phase trajectories were coming to that. And then you also get the other fixed points, which are like power law cosmological solutions, which you did not get in the earliest approach. So this is the advantage of the standard approach. And also the standard approach is regular at the GR limit, which is like the x goes to 0 limit, because just put x goes to 0 here, nothing diverges. And yeah, another advantage is, of course, power law cosmologies can be obtained. But the limitation, very serious limitations, this success of this approach crucially relies on the invertibility of this relation. Why? Because you want to get R in terms of y by z. What is that? Is not for a FR gravity that is not invertible. You cannot get R in terms of yz, and your whole approach fails. So then came another second approach to circumvent this limitation. So in this approach, these three dynamical variables are still there, but in place of the other three, you define some kinematic quantities. Why call these kinematic quantities? Because they depend on how the universe evolves, not what is the inherent model that is making it evolve that way. It's all dependent on h and its derivatives. N is, by the way, the logarithmic scale factor, log of a to the base e. And in terms of these kinematic quantities, you define three more dynamical variables. And here there are two auxiliary quantities. Earlier there was only one, gamma. Here there are two. And now we have two constant equation. One is coming from the Friedman constant, of course, as usual. Then the definition, very definition of the Ricci scalar also provides you another algebraic constant. So from the 6 dynamical variables, using two constants, we can eliminate 2. We are reduced to a 4-dimensional dynamical system, which is very much consistent with the earlier one. Earlier we have 5 dynamical variables, 1 constant. So again, 4-dimensional. But the thing is, now your h can be represented in terms of the dynamical variable a, and r can be represented in terms of the dynamical variable a and y. By the way, this m is any arbitrary constant of the dimension of h, which usually comes from the model. Now, for a given r, since you can write r in terms of the dynamical variables, for a given r, you can always write these dynamical auxiliary quantities in terms of dynamical variables, no matter how complicated it can be, but you can always write. And a very good example of it is the Husawiki model, which is like a very important FR model, very celebrated FR model for late time cosmology. And it has 3 parameters like C1, C2, N, and also M. M is a parameter of the order of Hubble parameter. I mean, sorry, of the same dimension of Hubble parameter. So 4 M is a character, or you can also say characteristic mass scale. So with the standard approach, this thing is invertible only when this n is 1. So you can only only investigate the n equals to 1 dynamics with the standard approach. But for the alternative, with this alternative approach, in principle, you can investigate the full general phase space of the Hus-Sawicki model. So this is the advantage. Also, of course, the disadvantage is the expressions are too complicated. Then now let's come to a dynamical system formulation that I developed during my past postdoc with my colleagues. So we still use the dynamical variables, all dynamical variables, and these are the standard dynamical equations. Here I have written all the 5, and that is for a reason. Next, we also introduce cosmographic parameters. They are again kinematic parameters depending on how the universe evolves, irrespective of whatever be the dynamics, because they are related with A and H and their derivatives. Then we have 2 observations. This auxiliary quantity gamma, which was kind of problematic when that invertibility issue was there, only comes as xy gamma. It comes in 2 equations here, xy gamma, xy gamma. And secondly, this xy gamma can be written in terms of the dynamical variables and the cosmographic parameters. So the dynamic, we can write the full set of dynamical plus cosmographic equations, where this n is again the logarithmic scale factor, log of scale factor, and we get this 1, 2, 3, 4, 5, 6, 7 dimensional system. You can go on still. And then together with the relation that xy gamma is this one. And now again we have 2 constraint equations. Like one is the Friedman equation, one is just the definition of the Ricci scalar. So with these 2 constant equation, we choose to eliminate 2 variables y and z. Why these 2 variables in particular? Because only these 2 variables in their equation has gamma. So right now the system we got is free of gamma, free of the invertibility issue. But now to close this system, we need to give a cosmographic relation between the cosmographic parameters, such that we can represent S in terms of J, K, Q, K, H, etc., and then it will be a completely closed system. What do you mean by giving a cosmographic relation? So you basically specify how the universe evolves. So you do not take into account any particular FR models. Say you say whatever be the FR model, I need my universe to follow this particular evolution for some kinematical consideration. And evolution of the universe, a particular evolution of the scale factor, can always be represented as a constant among the cosmographic quantities. So just get to an example now. So there was a lot of work regarding can an FR cosmology and FR gravity give rise to a cosmological evolution that can exactly mimic the lambda CDM model. And people have tried to reconstruct the FR gravity the form of FR which can do this, and it leads to a mess. So what we did is we understood that the evolution that lambda CDM model gives rise to can be specified by this necessary and sufficient condition in terms of this in terms of this cosmographic requirement. So our next step was, can we put this cosmographic requirement as a constraint on the phase space? So what we did, we have these three equations, and in where we have J, we just put in place of J, K plus 1. We don't need this equation. S does not even come in the picture. This is exactly what we have done. So this phase space corresponds to, we don't know what FR gravity, what is the functional form of FR, whose phase space is given by this. But I know that whatever be the functional form of FR, this FR will give rise to a dynamics that is indistinguishable with lambda CDM at the background level, not the perturbation, at the background level. Now, if we confine to spatially flat cosmologies, this again comes back to, reduces to 3D, because we make K the spatial curvature parameter to 0. Now, what are some important questions? Some important questions here, that first, can we get physically viable lambda CDM mimicking FR models? So people have got some functional form of FR numerically, but they are so complicated, they did not even bother about checking these two conditions usually. Or even if they tried, it's not so, result is not so illuminating. And secondly, suppose we get physically viable lambda CDM model, physically viable lambda CDM mimicking FR models. Can we distinguish this model with the actual lambda CDM model at the perturbation level? Otherwise, how are we going to know what's the model that's driving the universe? So ideally, to answer this question, again, one needs to reconstruct the FR theory, which leads to a mess. By that I mean the reconstructed FR comes in terms of hypergeometric functions. Of course, it's very tough to do perturbation theories, say, for example, with hypergeometric FRs. So it turns out we can provide an alternative approach with the reconstruction, the alternative to reconstruction method. The reconstruction method is just cumbersome. So here we have shown the phase space, the various projections of the phase space for spatially flat lambda CDM mimicking FR cosmologies. For the spatially flat case, this is 3-dimensional, and we have shown the projections. The 3 dimension is x, omega, and q, and we have shown the projections of the phase, the 3-dimensional phase space on these 4 planes, you can say. So q equals to half is when the universe is decelerated, q equals to -1 is when the universe is accelerated, omega equals to 1 is when the universe is matter dominated, omega equals to 0 is when the universe is completely dark energy dominated. Here dark energy means FR gravity, not lambda. And the shaded region corresponds to physically viable region, like this. So all the FR all the possible trajectories here corresponds to some possible lambda CDM mimicking FR cosmology. What is the inherent form of FR? I don't know. I don't even need. So this fixed point P3, this represents the matter-dominated epoch of the universe. And this fixed point P2 here, yeah, they represents the asymptotic future of the universe. So we see that, by the way, this asymptotic, this is a de Sitter point, and this is just a power law expanding matter-dominated phase. So we see that these asymptotic future, they always lie outside this shaded region. So we can conclude that for any lambda CDM mimicking FR cosmology, ultimately it will always lead to a state which is physically non-viable, in the sense in which either of these condition gets violated. Which one gets violated, we don't know, but one of them gets violated because this future asymptotic state is outside of this shaded region. So this is a good result that should be kept in mind for anyone trying to mimic lambda CDM model with FR gravity later on. And we should contrast, and we arrived at this conclusion without even knowing the functional form of FR. We contrasted this to Husawiki models, for example, which are always physically viable throughout, but they are not completely indistinguishable from the lambda CDM at the background level. Whereas for our case, these are completely indistinguishable at the background level, but they are they ultimately leads to a region at some point during the cosmological evolution that has some theoretical pathologies. And what about perturbations? So one of the important quantities for late time cosmology is what is called the matter density contrast. So this rho m is the dark matter energy density, and this delta rho m by rho m, which is also called delta, this quantity delta, this is called the matter density contrast. This is an important quantity in late time cosmology, and its evolution is governed, it can be shown that its evolution is governed by this equation. Now, what we observe that you can also write, sorry, this tau is same as n, logarithm of the scale factor, just, yeah, typo. What we observe that this whole equation can be written in a way which is also, I mean, such that all the coefficients arising here can be expressed completely in terms of dynamical variables or cosmographic quantities. And also, like, in fact, a couple of equations. So Z is like k square over a square h square, which a quantity which gives you either the super horizon mode or the sub horizon mode at different limits. So you can write this perturbation equation as these two equations. Now, for any trajectory whatsoever, you can numerically solve for x, omega, q, and z in terms of the logarithmic scale factor, and then also solve, and once you know this, you can also solve for delta n using this equation numerically. So you can solve how this matter density contrast evolves along a phase trajectory. In fact, you can also pinpoint on the phase space that which phase space point represents the present cosmological epoch. And since through any phase space point there only passes one trajectory, so it will be an interesting thing to see how matter density contrast evolves along this trajectory, because that trajectory represents a possible lambda CDM mimicking FR cosmology which has the present state of the universe in its course of evolution. Then you can calculate how matter density contrast evolves along that trajectory, and also then compare it with lambda CDM model to see whether there are any observational differences at the perturbation level. I mean, we have not done this work yet, just the outline is presented here. Okay, another example of what you can do with the cosmographic analysis. So in early universe, there is also, I mean, instead of inflation, there is also another contesting paradigm, which is called non-singular bouncing paradigms. In non-singular bouncing paradigms, there are a contracting phase, typically a power law contracting phase, which is also called the ekpyrotic phase, ekpyrotic contraction phase, that then comes to a finite size of the universe, not hitting a singularity, and then it starts to expand again. So people have tried to construct various bouncing solutions in various gravity theories, and one of the and also of course in FR gravity theories. And one of the main problems in constructing these bouncing cosmologies is various things just diverge in the contracting period. So let me just explain. So here I have taken an ansatz evolution. So I have specified that the universe evolves this way, and this represents a contracting phase that smoothly connects to a bounce. Why? Because when t is large, so think of this as t is very much negative. Then the universe was evolving like, since t is very much negative, it will be like minus t whole to the beta. Beta is a positive quantity. It's like a power law contraction. And then when you come closer and cross a threshold time called alpha, then the evolution is something like this. This you can just find by integrating this Hubble parameter. So it's like a contracting phase, ekpyrotic contracting phase, smoothly connecting to a bounce. And we saw that these specific evolution can be sufficiently described by this kind of a cosmographic constraint. Remember I said like all the evolution can be described by an algebraic constant over the cosmographic parameter. So here is this cosmographic constraint for this evolution. And if we consider a very a simple case where, I mean, this is spatially flat and vacuum cosmology, and concentrate on the contracting phase prior to the bounce, we will get this kind of a cosmographic, we will get this kind of a dynamical system. N is the log of A. So in the ekpyrotic contraction phase, which is like this one, a power law contraction phase, you have Q is something positive because you see like this, and as the bounce approaches, your Q, which is also called the deceleration parameter, that goes to minus infinity. And yeah, so as I said, some of the important questions regarding the pre-bounce contraction phase is whether these contraction phases are physically viable. which again means f prime and f double prime should be 0, or whether they are stable against small anisotropic perturbation. This is a very important issue while constructing bouncing scenarios, because if the anisotropy diverges so much, it leads to various kinds of instabilities. Again, to investigate this question, ideally one needs to first reconstruct what is the underlying FR theory that is giving you this kind of an evolution. Then you can calculate f prime, f double prime, and again how the anisotropy evolves, etc. But again, it leads to a mess. So is there a way around? There is, using this cosmographic approach. So we have analyzed this two-dimensional phase space, and we have arrived at this kind of a plot. Let me just explain a little. So earlier there was these two quantities, because it was a two-dimensional phase space. Oh, okay, I did not write what these quantities mean. Okay, but this x is just the same as this x, basically. Okay. Now I understand there are a lot of typos. And this q is again this basically this same q, the deceleration parameter. This u1 is something related to x, so you do not need to worry about what exactly is u1. It's just the transformation of the variable x by different transformations, and this. So you can think of these horizontal directions as the x directions, and these vertical directions as the q direction, and this upper boundary here is q equals to this thing, which represents the ekpyrotic contraction phase, and this lower boundary here is where q goes to infinity. Again, we use some variable transformation so that the infinity can be brought to a finite, like a finite quantity, like this q bar equals to this finite quantity. But the main point here, I would like to invite you to check this shaded region. So there are two kinds of shaded region. The first is, first of all, so all these phase trajectories, they represent a possible ekpyrotic contraction phase which starts from the upper boundary, leading smoothly to a bounce, which is like the lower boundary. All these phase trajectories. This pink shaded region, that corresponds to where the cosmology is physically viable. That means f prime and f double prime are positive. And this blue shaded region, like this one, or here this one, or here it's even shrunk. This region corresponds to the region which is free from anisotropic instability. So suppose a cosmology in the phase space is represented by this point, then if you take small anisotropic perturbation on this cosmology, it is stable, it decays. But a cosmology, suppose, is represented by this point in the phase space, or this point, then if you take small anisotropic perturbation on this cosmology, then the perturbations just diverge. So it leads to an instability. So we want a periodic contracting phase. That means a point, a fixed point. It's a phase, so it should be represented by a fixed point. And a periodic contracting phase, that means a fixed point on the upper boundary, which falls both on the red region and the blue region. That is free from both, that is physically viable, free from ghost or tachyonic instability, and also from anisotropic instability. But unfortunately, we see there is none. So we have, I have shown here the plots for 4 values of alpha. We have investigated for the full range. So these fixed point on the upper boundary, they are possible ekpyrotic contraction phase. But you see, all the fixed point, they just miss any one of the shaded region. For example, these 2 fixed points miss the red region. These fixed points miss the blue region. Yeah, this fixed point again just miss the blue region. It's always like this. So we arrive at the important conclusion that at least if you take such an answers, which is like a basic answers for contraction phase connecting smoothly to a bounce, irrespective of whatever the underlying FR theory that may give rise to it, I mean, this cannot be at the same time free from ghost or tachyonic instability or anisotropic instability. And we arrived at this conclusion without even knowing the inherent functional form of FR. Because if we wanted to know it, it would have been a mess again. So this should be kept in mind while someone else tries to construct physically viable bouncing scenario in FR gravity. Now, one might take a much more complicated ansatz and recover that they can get a physically viable bouncing scenario which is also anisotropically stable. Who knows? But at least for the simple answers like we just took, it is not possible. For a more complicated answers, this condition would be even more complicated. Okay, so now let me just summarize. I have, as I said, that classical gravitational theories are a kind of non-linear dynamics. So even in very special, I mean, except in very special cases like R-square vacuum scenario, we are not fortunate enough to exactly solve the coupled nonlinear differential equations, because as far as I remember, there was some exact solutions for R-square vacuum scenario. I forgot. And also, there is no unique choice for the dynamical system formulation. No unique phase space approach. You choose whatever suits the problem at hand. So these are the main 2 summaries, and for whoever who might be interested in this dynamical system analysis thing, there are 2 extensions which comes to my mind. So So mostly it is still used for to investigate the dynamics at the background level. Incorporating perturbations in the analysis is an important task, and these guys, they have mostly started some works in these directions, and even we are, I mean, I have some unfinished projects in these directions, and yeah, but it will be an interesting thing to analyze cosmological perturbations from various aspects using the dynamical system formulation or the phase space formulation. And another problem which might be very interesting, that is, if we can extend the dynamical system formulation to investigate dynamics of inhomogeneous spacetime. It's not easy, because for inhomogeneous spacetime you get partial differential equation. So somehow you have to reduce to some ordinary differential equations which you can work with, and it would have very good applications. And because two applications that comes to my mind is there are some models of inhomogeneous dark energy, which says that maybe we do not live in a perfectly homogeneous universe, we live in a void, and our universe is more described by inhomogeneous models like Lemaitre-Tolman-Bondy model. I don't know how much observationally viable these are, but there are models. And then, of course, another very important application might be if someone can develop inhomogeneous and dynamical system formulation for inhomogeneous spacetime and apply it to gravitational collapse scenario. Because gravitational collapse scenario is basically inhomogeneous, spherically symmetric. So we can extend from dynamical system formulation to cosmology, in cosmology to dynamical system formulation in astrophysics. So if someone is interested, one can see these works by Roberto Sussman. So this finishes my presentation. Thank you.
Okay, thank you very much for an interesting talk. If you have any question, please, it's time to ask question. Anyone?
In your second approach of dynamical analysis,
Second approach?
yes, the matter dominant fixed point is a subtle or unstable point.
The second, okay, the second approach. No,
Yeah.
no. The second means the standard approach.
Standard approach, matter dominant is unstable, right?
Matter dominated?
Yes, point is unstable. But for the second approach,
no, I have not considered matter dominated phase here. So sorry, I could not understand. I could not understand. So I have not considered matter dominated phase in the standard approach.
in the standard approach, you do not consider matter dominant.
Yes. In the standard approach, I did not show any example that has matter dominated fixed point.
So I may do something, but in which a pose matter dominated point is unstable. I hear
okay,
this.
okay.
thing.
So if you go to the lambda CDM, the phase space of lambda CDM cosmology, which is not FR, which is just GR,
Oh,
then
yeah.
if you take only the lambda CDM, forget about inflation also. So in lambda CDM, you have a dark matter dominated epoch or matter dominated epoch, which is the past, and then you have the dark energy dominated epoch, which is the future. So the phase trajectories come out from matter dominated the matter dominated fixed point to dark energy dominated fixed point. So matter dominated epoch is in the past and dark energy dominated epoch is in the future. That is when you do not consider radiation, because if you consider radiation, then there are three quantities: radiation, matter, and dark energy. And radiation came even before matter dominated epoch. So in that case, if you take that, then your radiation dominated epoch will come as an unstable fixed point where all the trajectories originate from, and then the matter dominated fixed point will be something like an intermediate state. So the phase trajectories will go towards the matter dominated fixed point, but then scattered away, because it's an intermediate state between radiation and dark energy. Then all the trajectories will end up in a dark energy dominated epoch.
If the point is unstable, can the system evolve to that point?
No, if point is unstable system, the trajectories can only originate from that point. But here, by unstable, I mean that you can think of like all the trajectories are getting away from this point. So this is repelling. So by unstable, I mean if you are very close to that point, not exactly on top, because if you are exactly on top, you will be on top. But if you are near to it, you will get pushed away of it. So it's like a potential maxima.
Oh, yes, but I think the good point should be the saddle. I think, right?
Good.
Saddle point. Saddle point.
Saddle point is
It's not a saddle.
No, it's not a saddle. Depends. Like if you take radiation into account, then it comes a saddle. If you do not take radiation into account, then it's unstable.
Okay, understand.
But it's like an intermediate state of the universe should always be saddle points.
And in your second approach, do you analyze the stability of the fixed point?
In my second
Second
approach,
your second approach of dynamical analysis, did you analyze the stability?
yes, I analyze the stability for phase space of R square vacuum cosmology. That is what I showed here. Yeah, because I have only included that one in my presentation because the phase space is two-dimensional, so I can show you plots. Otherwise, if it's three-dimensional, I cannot show you plots. So
and you also analyze the perturbation in your study, right? Perturbation.
Yes, yes. I mean, the most important is if you start investigating the perturbations, because nowadays cosmology cannot be restricted to only the background level.
And did you compute the primordial power spectrum?
Not yet.
Not yet.
We were supposed to calculate the how the matter density contrast evolves. So there are so we expected some difference between how the matter density contrast evolves in lambda CDM model and other models, FR models that are at the background level indistinguishable from lambda CDM. So like you have those things called there is a quantity called gamma, which is like 7/11 for lambda CDM. I forgot what's the name. Growth index parameter. Yeah, there is a quantity called growth index parameter called matter density perturbations. So that is an important cosmological observable. So it would have been good if we could calculate the the growth index parameter for lambda CDM mimicking FR models and lambda CDM models, so that we can distinguish. Okay, so this model is more close to what the observations show us.
Okay, thank you.
Okay, thank you.
Okay, is there any other questions? Okay. If not, I think it's about it is a good time to end the talk, to end this seminar, and please say thank you to our speaker again. Okay, okay, the talk is end. So I don't know much about it, but when you say FR model, when you say the model like R square or R, like